Hello and welcome again. This is Mrs. Rowe, and we're in chapter 3.4 looking at passive transport. This is video 2 that I'd like you to watch this week. Today we are going to talk about how and why molecules move in the direction that they do, and what I've created is something that I call Diffusion Mountain. It's just a nice little picture to help us remember how the molecules are moving and why they're moving the way they are. So at this time you should have your notebooks out, and I would like you to start by just drawing like I have here. This is our mountain, just a nice little parabola. And as you get our mountain drawn, you can just title it at the top, but leave some room at the space. We're going to put drawing some little people in here as we go. So today we're going to be working on the right side of our mountain as we talk about passive transport. And then in a couple of days, we're going to come back to this drawing in your notebooks, and we're going to do active transport on the left. Okay. So go ahead and hit pause at any time, and then when you're ready to move on, just come on back. So the top of the mountain represents a high concentration. It could be a high concentration of water, making it hypotonic, or it could be a high concentration of solute, making it hypertonic. It just depends on what is the molecule you are following and how you predict that molecule is going to move across that membrane. And down here is your low concentration. Again, is it a solute molecule? Is it the water molecule? It doesn't matter which one you are talking about, as long as you are clear on that. Most of the time we're talking osmosis, which is movement of water across a membrane. Diffusion is, we need to talk about diffusion, the random movement of molecules from high to low. So this week I had you do a quick simple little demo where you took something like perfume or body spray or something and sprayed it in the room. And did that odor eventually spread throughout the space until somebody on the opposite side could smell it? How did that happen? That is known as diffusion, where the molecules are moving randomly from a high concentration to a low concentration. That is just how diffusion works. You're going from um, it's I always think of it as when school lets out, the kids are going from a high concentration inside the school building, and the bell rings and they all leave and they diffuse out. They spread out. They go from a high concentration to a low concentration as they all go running out of the building. That's just the nature of how molecules behave, and we're going to see how cells take advantage of that and use that to their advantage. So a couple of things we need to get down as we look at passive transport and how we work. Passive means no energy is needed. It is simply driven by simple diffusion, how molecules are going to move. And one of the things that's going to drive simple diffusion, so let's get some of our vocab down here now. No energy needed because it is driven by diffusion. Diffusion is what drives this process. If we're talking about diffusion specifically of water, then we will be talking about osmosis. But otherwise, if it's not specifically water, we use the term diffusion. Please remember that osmosis is diffusion. It's just a specific type of diffusion. Okay? So that is what's going to be driving our process today. So let's start with this. When we are looking at our cell, inside the cell, outside of the cell, we're talking about two different concentrations across the membrane. When there is a difference in those two areas across the membrane, inside and outside, when you have a higher concentration on one side and a lower concentration on the other side, we call that a concentration gradient. So a concentration gradient is just a term that refers to the fact that there's a difference in concentrations. And it is the concentration gradient, this difference in concentrations, that's going to drive these molecules to move. It's the how, it's the why. Water is going to enter or leave the cell, or we saw the egg, the sugar went into the egg, making it darker, or when I did the chocolate syrup, it made the egg darker. So that's because of this concentration gradient driving molecules from a high concentration to a low concentration, which is just diffusion and how molecules behave. And this does not take energy. As you saw when you sprayed your perfume, it simply just goes on its own. So the way to remember this is we're going to draw a little person at the top. And my little person, just a little stick person, nice and simple. So we're starting on one side of the membrane at a high concentration. This is my little person. And my little person is going to be holding my molecule that's at a high concentration. It could be a water molecule. Like I said earlier, it could be a sugar molecule. It could be a salt molecule, or not salt, can't be molecules, but that's besides the point. It could be salt, it could be sugar, it could be water, whatever it is that's at a high concentration. And this is what's important to remember. Passive transport will always move in the direction from high to low. Okay? So if I'm standing at the top of a mountain and I am holding a round ball and I drop the ball, what will it do? Force of gravity. It's going to roll down the mountain from a high concentration to a low concentration. It's just what it's going to do. I did not have to put any energy in it. I simply dropped it. That is what happens in passive transport. The molecules will simply move. They will simply fall from a high concentration to a low concentration. That is driven by that difference in concentration. And eventually, they're going to get to where we reach equal concentrations. Do you guys remember the term for that? Isotonic. And we call this the land of equilibrium. When we get to the land of equilibrium, movement doesn't stop. Our molecules are in constant motion, but there's no more change in concentration. We've reached isotonic equal concentrations. There's no gain or loss of mass. There's no gain or loss. There's an equal movement in both directions. So the land of equilibrium, once this concentration gradient has moved passively to this level, all cells are going to try to reach equilibrium. So when you put plant cells in water, they're trying to take in water until they reach equilibrium. When you put plant cells in salt, well, the water leaves the cell trying to reach equilibrium with that saltier environment, causing them to lose water. So unless the cells have a way to block that flow, the molecules are simply going to move from high to low concentration, whether it be water from high to low water or sugar from high. We saw in the egg and syrup, there was more sugar in the outside in the syrup than there was in the egg. So some of those sugar molecules went from that high concentration in the syrup into the egg where it was low, and filling our egg up with sugar. So that's passive transport. Oh, one more thing to remember, I almost forgot, is that the greater your concentration gradient, the faster things are going to move. So I'm going to put a little ledge here, a little cliff on our mountain, and I'm going to put another person on this little ledge. Oops, he's going to have an extra leg. And very hard drawing with a mouse. Okay, so our little person here is also going to be given a molecule. And notice the difference. The concentration gradient is much smaller. It's not as big as the first one. This person's also going to drop the ball. If they were to drop the ball at the same time, which one's going to pick up more speed, is going to accelerate faster? The one that's going at a steeper, bigger distance, or the one that is shallower? Obviously, as you start to reach equilibrium and your concentration gradient gets smaller, the rate of this change slows down. The bigger the difference, the faster the molecules move. As your concentration gradient gets smaller, the molecules move slower until they reach equilibrium. Okay, so we're going to be looking at some of the factors that are going to affect the rate, and that's the last thing I want to leave you with, if I can find it. Trying to remember if this is it. Here it is. So the rate of diffusion. So the rate of diffusion is how fast are those molecules going to move. This is the last piece that I want you guys to get down. The rate of diffusion depends on how steep that concentration gradient is, what we just discussed. Temperature, think about it. The higher the temperature, the faster molecules are in motion. So that's going to affect rate of diffusion. Polarity charges, we're going to talk about that later, and diameter of the molecules. Obviously, small molecules are going to be able to cross the membrane faster and easier, and that's where charge comes in. That's going to be tomorrow. We're going to talk about the cell membrane and how that becomes a factor in making things semi-permeable. So the cell membrane is not going to allow everything to simply diffuse across. Some things are too large to diffuse across the membrane. So regardless of how big that concentration gradient is, if they can't get across the membrane, nothing's going to happen. So these are some of the factors to be aware of that are going to drive how fast diffusion occurs. So that's it for today. Diffusion Mountain and passive transport. Hopefully this makes sense, and if you have any questions, please feel free to ask. Until tomorrow, we'll talk about the cell membrane, and then we'll talk about the other side of the mountain and active transport on Friday. See you later.